So, welcome back, friends. And as I told you, today I start talking to you about the frictional forces and their manifests, which are not basic things, but which are rather experimentally determined things. A kind of relationship which we call empirical relationship, which depends on certain experiments done and results obtained. So before I go straight away to the friction, which is the manifest of electromagnetic forces, I'll just revise for us some common forces which we use in mechanics and mechanical calculations. So, for example, the two forces which are fundamental in nature, the gravitational forces and the electromagnetic forces, which are rather all-pervasive, which are present everywhere, and interestingly, no intervening medium is required. Medium not required, which means that they can exist across very high level of vacuum in the interstellar space, intergalactic space, anywhere in the universe. And the two basic fundamental laws, basic fundamental forces, which are long range forces. I'm not going to talk about the short range forces, which hold the nucleons in the nucleus, which are responsible for their radioactive decay, etc., etc. Now, one of the things which we are going to focus in the friction are contact forces, when two bodies are in contact. Contact forces are solid contacts and fluid medium contacts. Fluid is a term which we use collectively for the liquids and the gaseous media. Now, an example of the contact forces is a book resting on a table. Okay, this could be here. I am just showing it to you that if this is the table and then this book is resting on the table. Right now on my left palm it is staying where it is, and in the frame of reference that we have, we look at it is in a state of rest, which means that presently the book, the pair of forces which is acting in the book, one obviously in the downward direction due to the gravitation, and the other is the reaction of my palm right now in the upward direction, which we call the normal force. The normal force is a force which acts on the surface of the contact, because if you talk about why it is there, the book is also putting a normal force on my palm. So, yeah, another example is a system of rigid bodies, bodies which are not changing their shape or size, etc. These bodies are connected by thin rods, hinges, etc., etc. Okay. Now, while dealing that, what we go for is mutual contact forces. Like I said, for each pair of bodies, right now the two bodies are the table and the book. So for each pair of bodies, there is a mutual contact force. One body is having a contact force on another body, the other body has a contact force on the first body. And this is satisfying third law. What does that mean? Means F12 is equal to minus F21, or F12 plus F21 for the pair of the bodies is equal to 0. Okay. Normal reaction is always normal with the solid contacts. Okay. Like in this case, the normal reaction will be upward for the palm putting a force on this, or the tabletop putting a force in the normal direction. So the normal reaction force we call with solid contacts. We have to understand that. Also, in the case of fluids, when the contact is with fluid, gaseous or liquid mediums, then there is a buoyant force. There is a buoyant force, and that is equivalent, remember, eureka, okay, that is equivalent to the weight of the displaced liquid. Whatever is the weight is equal to the mass of the displaced liquid divided by the, multiplied by the acceleration due to gravity or the gravitational field, whatever exists over there. The buoyant force of fluids is another thing when we do fluid mechanics. Now, in the course of time, we talk about strings. Strings and tension in a string. The tension in a string, if it is a stretched string like this, the string, and we stretch it with a force in this direction and another equal force in this direction, then this string is under the state of tension. And as I told you, the tension may have, for the same point under consideration in the string, the tension is in this direction as well as in this direction, and the two of them are equal to each other. It is for us to decide which direction we take, like it will come in the due course of time, and you will understand that. So tension in a string. This string is normally taken as inextensible. That is, it is not possible for us technically, theoretically, that the string can be elongated or it can be compressed. Now, next thing which we may encounter is the force due to a spring. The force due to a spring, that if I have the spring attached to a rigid body which cannot be deformed, and I say that under the condition of a force etc., if I apply a force F, there is an extension of the spring, say X. Okay, but is it possible for a single force to extend the spring? The answer is no. It always requires a pair of forces, and this actually is applied by the rigid body in the opposite direction, and everywhere on this spring the net force after extension is equal to 0, because this spring is not moving. So the net force at this point or this point or this point or whatever point, and the spring has a relation which is because of elasticity, which says that the force is proportional to the extension, okay, or the compression, which is equal to x, the deviation over here from the original length of the spring, and so that my force is equal to minus kx, where k is the force constant, and the force constant k extends to infinity for inextensible springs. The mass of the spring under condition, when we deal with that, is taken to be negligibly small. So all these cases, the spring, the string, the buoyant forces are normal contacts, mutual normal contacts, etc., etc. We require to investigate, to try to understand how these forces they function and what is the relation with the, if there is an extension or if there is not extension, I said, and therefore what we say is that friction, which we are going to discuss in the following, is rather a manifest of electromagnetic forces. In the electromagnetism, we have a body, and the body is composed of molecules, atoms, etc., etc., and they have their own charges distributed all over the body, working, each atom applying a force on every neighbor, and they have their own neighbors and this and that, and which is the subject of solid state physics. But ultimately, what is there, much before the study of electromagnetic forces in the form of electrons, protons and neutrons, we had the frictional forces, which were established with the help of certain experiments I'll show to you, and certain empirical relationships. Empirical, this word is important. You can go to your dictionaries, and it's not only used frequently in physics, but it is used frequently in all walks of life, particularly in chemistry, etc., etc. Okay, so next we talk in detail. I try to introduce the concept of friction. So the most beautiful thing in nature is friction. It is friction because of which we can move on a surface which should not be frictionless. It is friction because of which our cars move. And I will come to that beautiful concept of the invention of wheel, where the friction is minimized with minimizing the contact, and that is the friction of rotation, is a beautiful concept. But to introduce it in a subtle way, I will go for static friction, which opposes impending motion. How come? I take a block, maybe a book, of mass m, placed over a rigid horizontal surface, and here I show that this mass is kept on this surface, and there are a pair of forces. One is the force which is because of the table or because of the surface, whatever, which is the normal reaction force, and there is of course a force because we are doing the experiment on the surface of the earth. So due to the gravitational field of the earth, there is a force mg down towards the center of the earth, mass of the center of earth being the mass of the earth. Okay, so we concentrate on that point. What happens now? What we do is we apply a force on this body, this mass, and we see that while we are applying the force, the body is not moving. Strange, because Newton's second law says that if a force is applied on a body m in a free space, or in case it is put on a frictionless surface, then immediately Newton's second law will pop up and say, I will tell you about what is going to happen, and will tell you that F is equal to ma, so there is an acceleration and that will result in a velocity, etc., etc. There is the case, but here we are taken aback. We don't understand in the beginning what is happening. I am applying the force on this body and this body is not moving. So that means I am applying a force here, but the body is not moving at all. It is in a condition of rest, which means that there is another force which is acting on this body in the opposite direction, which does not allow the body to move. And this force, parallel to the surface of contact, is equal to this force. Let us increase this force. And the opposition also increases because the body is not moving. So that means the force that I am giving over here is Fs, which is the static force. The velocity is still equal to 0, and this force keeps on increasing as this force is increasing until a time t is equal to 0 minus t is equal to 0 plus, both of them are equal. It happens that after that, if we increase the value of f little bit, then after that limit has been achieved, the mass starts moving in the direction of the force, and we can thereafter we can see what situation comes. The situation comes that the motion of this body relative to the surface, the horizontal surface over here, this happens, and the body achieves at a further time a velocity, also an acceleration is possible. At that moment, still there is a frictional force, but this frictional force is smaller than the frictional force that was here when the body was starting to move. This we call the frictional force, the kinetic friction, Fk. And Fk, we can also call it the dynamic friction. Okay. And thereafter the body starts moving, there is an acceleration, there is a velocity, etc., etc. And the net force on the body at that time, if the value of Fk remains the same, and it doesn't depend upon the velocity, it doesn't depend upon the acceleration. In that case, the total force on this body which is in motion on the surface, this force becomes equal to this force F minus Fk. Okay. So we find that the maximum static frictional force that exists over here, empirically, by conducting experiments, we found that this is proportional to the normal force. The normal force which results because of the mass of the body, because the normal force is equal to mg. So Fs maximum, it is proportional to the force. One force is proportional to another force. And if taking to the linear system that we have been talking about often, then what we found is that the relation between Fs maximum and the normal force, this is a straight line. Slope is the same everywhere, and the slope turns out to be equal to what we are going to call mu s, the coefficient of static friction. Okay. So Fs maximum is equal to mu s into n. Of course, this n and mg are one the same thing, and thereafter we see that in the case of the kinetic situation where the body is moving in the velocity and acceleration, etc., etc., this equation exists, that Fk becomes equal to mu k into n. Now the interesting thing is that mu k is smaller than mu s. That means the frictional forces when the two bodies are in relative motion, they drop, they decrease. But the thing is that the friction does not depend upon the area of the contact, which means, like I told you, where is the book? If I put the book, the block is put like this, okay, the surface area is the maximum, then the block is put like this, and the surface area is less, or the block is put like this and the surface area is the least. The surface areas are changing, the mass of the body is changing, it remains the same. And when we conduct this kind of thought experiment or actual experiment, in reality, what we find that the friction does not depend on the area of contact. The friction does not depend on the area of contact. Okay, it rather depends on the nature of the surfaces in contact. The two surfaces, the surface of the body and the surface on which this is kept. Okay, so experimentally we find that the friction, whatever, dynamic or static, both the frictions do not depend upon the area of contact. They rather depend upon the nature of the surface in contact. Okay, now suppose I am just writing the same kind of relation which we are doing here for the Fs maximum. For the condition of t is equal to 0 minus and t is equal to 0 plus, which both of them in our case are equal to 0, and the body is with impending motion, now comes into motion. While in motion, we again have a relation like this. This Fk is again proportional to this, and we will have drawn it here, Fk here, and then the friction that will come out will be less than that. So I will just try to show it to you that in that case my slope here will be less, and of course this is Fk. So Fk as a function of n, will plot that the slope is mu n, and the slope is less as compared to slope over here. So mu s here the slope I'll get is mu dynamic or mu kinetic, whatever you want to write, we are free to write that, and then Fk is equal to mu k into n. And now what I suggest is that we remove the applied force. The body is in motion. The body has a velocity, the body has an acceleration, then this acceleration is determined by this relation. The acceleration will turn out to be equal to minus times the force, because it is retarding, so it is a minus sign here, then Fk upon m. So Fk upon m, it shows, now we can apply the relations of motion that we obtained in the kinematics. V is equal to u plus at, s is equal to ut plus half at square, and v square is equal to u square plus 2as, etc., to determine how long it will take to stop, how far it will take to stop. No? You can be asked to calculate the value of time, you can be asked to calculate the value of length, okay, etc. Depending upon the velocity what we have, this body is going to stop after some time, because of the beautiful thing that we have in nature. Because of the beautiful thing that we have in nature, which is opposition. Opposition to any motion, opposition to any activity, it gives us life to live, and therefore the only thing that we have to bear in mind is that the frictional forces are always parallel to the surfaces in contact. They are, but they bring about motion, they stop motion, they help us live our life. Because you have seen that if you want to move or run on a slippery surface, a surface with a small amount of friction, then of course you are going to have untoward things, unwanted things. You may not be even able to walk, you may slip, because walking, etc., that is a manifest of the friction. That is the beauty of our creation, the friction which we learn through the empirical relations that we have. So this is an introduction to the nature of friction and what kind of relations we obtain for these frictional forces, etc., etc. We will, in the next lecture, talk about certain problems, try to solve those problems and find out how the various manifests of motion are obtained there. Okay, I hope you have enjoyed. Think, man, it can give you a lot of insight into the beauty, how we live, and how friction is so very helpful to us. Thank you very much for being with me. See you soon.